Welcome back, everyone. And those of you who are joining for the first time, welcome to you to this series. Even if you are attending this without attending the previous ones, you would still find it useful because every session is structured in a way that it focuses on one concept. So this series, as Karan mentioned, has been a 6-part tutorial combined with a webinar that primarily covers deploying and managing containerized workloads. So we started with Docker. We looked at multi-container applications. Then I introduced Kubernetes. And last session was taking a closer look at Kubernetes and understanding the primitives. This session is the most crucial one, where I connect the dots by bringing all the concepts that we have explored so far into one. So by end of this session, you'll actually package, deploy, scale a microservices application. So we'll go from source code to a production application in 45 minutes flat. So this is going to be an interesting one. At the same time, as I mentioned, it's a crucial part of the series where I bring everything together to help you understand how to take applications and deploy them in Kubernetes as microservices. While a similar concept was covered in the previous one that was not based on a scenario or use case, I focused more on Kubernetes primitives like pods, labels, nodes, and so on. Here, I'm going to go back to the very initial scenario, which was the node.js and MongoDB application that we explored in the first 2 webinars. I'm going to bring it back and help you understand how we package and deploy it as microservices in Kubernetes. So the concepts that I'm going to explain are primarily related to microservices, while the demo is all about putting everything together. So I hope you're having as fun as me in being a part of this series. So let's get started. I'm going to talk to you about a methodology for developing contemporary new breed of applications, and they're called the 12-factor applications. While this concept in itself is pretty comprehensive, I want to touch upon that, and I'll leave you with the link where you can explore further. But it is very important for you to understand what makes a 12-factor app. Then we'll understand what are microservices, and we'll take a closer look at the key attributes of microservices. And finally, we package, deploy, and scale microservices in Kubernetes. So there is an interesting demo towards the end of this session where I'll walk you through all the steps it takes to go live in Kubernetes. So what exactly are microservices? So it's very important for you to appreciate and understand what microservices are before you delve into Kubernetes. So let me give you some background and help you visualize how microservices are designed. If you have been in the industry for a while, you know the 3-tier architecture has been a very popular, a very well-known design pattern for developing scalable applications. In 90s, when I started my career, this was a very emerging, trendy concept where client-server architecture was getting completely replaced by a 3-tier architecture, and internet was the basic factor or the driver for this architecture. So the UI is basically the browser. The business logic is where you'll write your J2EE or .NET or even PHP applications, and the data would contain your typical Oracle, SQL Server, or DB2 database. J2EE made this a very popular design pattern. So you could write your business logic in enterprise Java beans, write UI in Swing or JSP and servlets. Data would be typically in Oracle. And if you come from .NET background, the business logic was written using COM, ActiveX, and .NET. And the UI was all about ASP and ASP.NET. Data was about SQL Server. So it's a very well-known, very well-used framework. But this architecture doesn't align with the way cloud functions. So where is the misfit? Where does it break when it comes to cloud? So let me give you an example. The business logic is always deployed to what is called as an application server. Application servers typically run J2EE or .NET or any of the other middleware. and they're responsible for running your business logic as components. So here what you see as C1, C2, and C3 are essentially set of components that are designed to handle one functionality or one piece of functionality. Think of them as enterprise Java beans or .NET DLLs or COM libraries, anything. Now, when you're running an application in this mode, let's say there is a bottleneck. You're an e-commerce portal, and there is currently a campaign that is running where you are seeing a lot of traffic hitting your portal. Now, since the campaign is all about a specific time window where people get discount, people are checking out what is the price. They're actually not buying, but they are hitting the portal to compare how cheap is the product during the campaign window. So one of the components of our application server is responsible for the catalog, which is basically pulling the product information and showing the price. And remember, people are checking out and people are basically doing window shopping online. So let's say C2 is responsible for the catalog, and that is what is being used heavily. So when you profile your application and when you inspect what is consuming the maximum resource, you would notice that C2 component is basically responsible for the consumption of resources, and every application server is running at 90% utilization. And out of that 90%, 85% is consumed by C2 because that is constantly pulling the catalog information and rendering that in the browser. Now, how do you address this? How do you make sure that your web server is not choked or your app server is not really breaking? So you'll spin up multiple app servers. So you will run multiple VMs where your application server is running. But every time you spin up a new application server, you'll also end up creating C1, C2, and C3 because all of them are packaged as one application and they are deployed in one application server. So every time you multiply the number of application servers, you are basically multiplying the number of components that run inside the application server. But effectively, this is not helping you because ideally, I want to reduce the number of C1 and run more of C2 because that is what is currently required. The other example that I want you to visualize is Tatkal booking, right? So during the window of Tatkal, there are more number of bookings made than someone checking their PNR. So let's say Indian Railways has a component for PNR status and the other one is for booking. Obviously, during the Tatkal booking window, there are more number of requests and more number of resources consumed by the booking component than the PNR component. So if only Indian Railways can scale the application by spinning up more and more Tatkal components responsible for booking those immediate tickets, the website would be more responsive. But it may or may not be using an architecture where you can selectively choose a component and scale it out. So this is the traditional architecture, and VMs are being used as application servers, and every time you want to scale, you will spin up a new application server, and in that process you are spinning up other components which are also consuming resources, and effectively you are not able to solve the problem because you're not able to multiply or scale the actual component that is responding or responsible for this performance. Now, when you look at the emerging microservices architecture, you'll notice that the application server is now looked at the cluster level. So it is now becoming a pool of resources. We don't have one VM or one physical machine. Instead, we have the cluster of application servers where we are able to access the aggregated number of CPU cores, memory, and storage. And then on top of that, we actually run nodes, right? And these nodes could be physical or logical. Or they could be even, if you're familiar with Kubernetes, think of every node like a pod, technically, because it is actually containing multiple containers. So you are able to scale pods very rapidly. So this is purely logical. At this point, there is no mapping to Kubernetes or any other container orchestration engine. This is just to highlight the fact that in microservices, we don't scale one application server or one VM at a time. Instead, we scale the actual component that is responsible for handling the request. So in this case, you'll notice that we are running more number of C3s, component 3, because let's say suddenly everyone is realizing that the window is going to close and they started to buy the products. So suddenly the traffic has now shifted to the shopping cart and checkout component. So at that point, you should be able to scale out the shopping cart and checkout component and make them available so that the traffic is now evened out across your portal or your e-commerce site. So we end up running more of C3s because people are actually buying and checking out, and we need to make sure that that experience is smooth. And later on, when the window closes and when the traffic subsides, when the load evens out, C1 and C2, C1, C2 and C3 might be again running in even numbers because now we need everything, and it is basically balanced. So the fundamental difference between the monolithic architecture, by the way, this is called monolithic because each of AS1, AS2, AS3 is a monolithic. It is a black box, and every time you launch this new black box, you end up pretty much running everything that is packaged inside that. So this is monolith or monolithic, and this is microservices. So in microservices, we selectively choose what component or what service we want to scale, and we independently scale that. The number of CPU cores, memory, and storage won't change. We cannot directly influence that. But how do we maximize the resource utilization without compromising on performance? So imagine you have 3 sliders to adjust C1, C2, C3 performance. So dynamically, you can drag C3 when people are checking out and bring it back and drag C2 to the extreme right, where you have maximum number of C2s, which is responsible for catalog. And when everything is normal, when the traffic subsides, you can bring them back, and all the services are now evenly running. So that is the beauty of microservices architecture. If it is not very clear, let me explain you how this is going to be architected. So microservices are basically it's a design pattern where a program is broken down into individual services, and each service is responsible for one and only one task. For example, you want to send out an alert. That alert service is written independently. You want to write the logic for checkout. That is written as a service. And shopping cart is going to be another service. The databases required for each of them are going to be, again, stateful services. They are going to be coupled with some of these. And every microservice will have its own persistence, its own database. We are not going to have a centralized database. That's another difference between monolithics and microservices. And microservices are completely independent and loosely coupled, which means S2 can exist with or without S1 and S3. There are no dependencies. There is no absolutely any kind of prerequisite for a microservices to come up. You can deploy microservices and launch them independent of other services, and they discover each of them at runtime. For example, a microservice that is responsible to send out an alert. At one point, you could be running a microservice that is sending out an email, and later on, you can replace that with an SMS alert without disrupting or without changing anything else. So you can easily upgrade each of these services without disrupting the whole application. What it translates to is better reliability, better scale, and availability of your application. And each of these services are treated independently, all the way from the code. So when you're writing your microservices application, you will have a very well-defined pipeline where every service is managed independently. So you have different code repos that are compiled, built, released and managed independent of other services. And these microservices are loosely coupled because they talk to each other over queues or any other asynchronous pattern. There is no hard and fast rule that you got to make them asynchronous, but that pattern will make your applications more scalable. So Kafka, RabbitMQ, and some of the other message-oriented middleware are being used as the message channels for services to talk to each other. So what are the key attributes of microservices? First thing is servers are disposable. You will never have to debug a server when it fails. Instead, you simply launch another server and continue to work. So you will never have to deal with server level issues because servers are inconsequential when it comes to microservices. They are just the infrastructure layer, but we don't really care about a server, because if a server fails, we don't fix it. We simply kill that VM, launch another, and our application continues to run. So servers are absolutely disposable. There is no state, there is no affinity, there is very little dependency on one server or the other. So servers can come and go, but microservices will continue to run. Services are autonomous. Now what it really means is this: they are completely independent of each other. They continue to exist whether or not other services are running or not running. It doesn't matter. If you're familiar with service-oriented architecture, microservices is so much like fine-grained SOA. It is SOA done in a lightweight fashion. It is how SOA should be implemented, more developer-friendly, more practical, more doable, and aligned with the web scale architecture. As I discussed earlier, microservices are loosely coupled. They talk to each other using a variety of mechanisms, but you will never have to call one service from the other by hardwiring the location or the service name. That's not the idea. They should instead discover each other at runtime and continue to talk to each other. They are upgraded independently. This is the beauty of microservices. For example, S1 can be updated independently without disrupting the application. So let's say you're already running V1 of S1 and there are 10 instances of these microservices. You can now deploy V2 of S1. They'll also run 10, but gradually you will start fading away V1, and eventually when there are no connections and when there are no active consumers of V1, you will kill V1 and V2 will be replacing V1. It's actually like a rolling upgrade. So you can perform all of that on any microservice without ever disrupting the entire application. In monolith, when you have to do an upgrade, there is a definitive downtime, because you got to bring down the server, deploy the whole application, and then bring it back and register that with the load balancer. So it's a very different workflow. In microservices, you can continuously push updates without ever bringing down the actual application. So that is one of the powerful aspects of microservices. And finally, microservices use HTTP or a lightweight protocol for communication. Again, there is no hard and fast rule on what kind of protocol these services use. For example, S1, S2, S3 are talking to each other. They could use HTTP with JSON serialization, or they could also use gRPC with protobufs, which is more efficient. It's a binary protocol created by Google and becoming very popular. Or they could also use another protocol called NATS, which is again a very well-known emerging technology for microservice communication. So they can use any of the protocols. That doesn't really matter, but the idea is to make sure that the communication is lightweight and it is efficient. You can even use some of the older technologies like RMI or RPC or .NET remoting, but they are very platform specific. That's the reason why it's better to use more of an industry standard and an open source technology, like JSON with HTTP or gRPC, or as I mentioned, NATS. Some of those are better candidates than using the proprietary ones. So those are the key attributes of microservices. So what is a 12-factor app? Well, this session is not about how to architect 12-factor applications, but I want to briefly touch upon this before I take you to the demo part. So sometime in 2012, the founders of Heroku, which is a very well-known platform as a service offering, came out with the best practices of architecting applications for cloud. At the time, it was primarily targeting platform as a service, but the fact that it is relevant today is that it is very, very well thought through architecture. So what it basically advocates is a set of 12 rules. So code base, for example, you should always use a code base in a revision control or a source code control system and version it and then perform multiple deploys from that. How do you manage dependencies? Never hardwire your dependencies into your code base. Instead, declare them so that you can always perform the dependency installation independent of your code base. For example, the package.json in node.js or requirements.txt in Python or a Ruby gem, is an example of how dependency should be managed. Configuration should be stored in the environment. It should never be hardwired. So when the application wants to discover the database endpoint, it looks up the environment and doesn't read from a registry or an INI file. So that is what is config. Similarly, backing services like databases and cache, message queues, and so on, they should be treated as attached resources, and they are completely independent of the actual microservice. So you bind them at runtime, and they'll start discovering and consuming this. Similarly, there are a variety of these principles that are very well used, and this 12-factor app methodology got a lot of credibility, and it is highly relevant in the microservices and cloud native world. So if you are interested in learning this and applying it to your microservices, please visit 12factor.net, and you can actually learn more about each of those. Again, as I mentioned, this session is not about 12-factor apps. I could spend a couple of hours just explaining each of them, but the idea is to show you that microservices are aligned with the 12-factor app principles and leave you with the pointer so that you can explore further. So I set the stage for microservices. Until now, we haven't really dealt with microservices technically. The reason is I wanted you to get familiar with the Kubernetes terminology. So with the information that you have, like pods, labels, replication controllers, services, and some of the other primitives, you can relate to microservices better, particularly when you're targeting Kubernetes. So the idea is, now that you know what is Kubernetes and you know what are the principles of microservices, we'll apply both of them and target a microservices application on Kubernetes. So let me take you to the demo. All right, so first things first, I'm actually running a 3-node cluster on DigitalOcean, and this is set up using StackPoint. The third part of this series was all about setting up and configuring Kubernetes on DigitalOcean. If you're wondering how to do this, we have a step-by-step guide available. So I strongly recommend you to go back and look at the step-by-step guide to configure Kubernetes on DigitalOcean. So once you have this and configured the CLI for your development machine, you can verify the installation with kubectl get nodes. So there are 3 droplets that are mapped to 1 master and 2 workers. So this is the setup that we have, and we don't have anything at this point. This is a blank slate. The goal is to take our source code and run it on Kubernetes. Okay, we don't have any services, we don't have any pods. So here is the application. This is available on GitHub, and if you want the link, just wait for the tutorial to get published and you can access this. So within the app directory, you will notice that we have the node.js application. So this is a very simple to-do application, and it has the app.js and also db.js. db.js talks to MongoDB. So this is just to recall and recap what we covered in one of the earlier sessions. So it's a mean application. It is basically MongoDB, Node, Express, and Angular. So this is the application that we are going to package and deploy to Kubernetes. All right. So once we have the source code, we need to turn this into a Docker image. How do we do that? Well, we write a simple Docker file. And again, this was extensively covered in one of the previous sessions, but I'm just doing a recap because this session is all about connecting the dots and bringing everything together. So this is the Docker file. And what we are essentially doing is creating a Docker image with the source code that we have here. So we are moving the source code from our local directory, which is the app, to the container image. Then we install all the dependencies with run npm install. And then we have cmd node app.js as the initial command when the container comes up. So with this in place, all I got to do is to build the image. So the commands that you're seeing in my script file is a part of the tutorial. So you'll actually be able to repeat all these steps. So when we actually run docker build, it is going to quickly create an image and tag it. So it is now tagged with my first name /todo latest. So that is the image that we got. So when you actually do a Docker images, I have many images, but the topmost should be what we just created. So this is the one that we ended up creating from the Docker file. Excellent. So with that in place, now I need to do a Docker push. So I can do a Docker login with my username and the Docker Hub password. So this is going to authenticate me, and after that I can do a Docker push with the image that we built earlier. Right? So this is going to simply take the image and push it to the Docker Hub. The reason is we want our Kubernetes cluster that is running on DigitalOcean to be able to access the image. So what I built on my dev machine should be made available to the Kubernetes cluster. And the only way I can do that is to move it into a more centrally accessible registry. And that's what is Docker Hub all about. So now our image is available in Docker Hub, which means we can now start packaging and deploying our application as microservices. Excellent. So now I go to this directory called Kubernetes, and you'll see a bunch of artifacts as YAML files. So the first thing that I'm going to do is to deploy MongoDB, because that is our backend. So let's take a look at the dbpod.yaml definition. This is pretty simple. In fact, you would have seen this earlier. This is nothing but a pod, and this pod has a label called name Mongo app to do app. It exposes the default MongoDB port, which is 27017. Because we want the pod to write to the underlying file system, we are exposing a host path. More on this in the next session where I cover persistence and durability. At this point, just understand that we are adding an additional mount point so that the MongoDB data is written to the host and not within the pod. So that's all. We are pulling the Mongo image and exposing that on port 27017. So that is the port on which we are going to make this pod available. So let's go ahead and create the first pod of our cluster, and we can verify the creation with get pods. So here this is still getting created. It will take a couple of minutes because it has to pull the image. So I'm going to put that in watch mode, and we'll notice that the container status will move from creating to running. And as soon as this is running, we'll be able to deploy the other pods as well, because the database pod is storing the data. So our web pod should be able to talk to it. There we go. So now the DB pod is up and running. How do you check if this is running fine? Well, we can use kubectl logs followed by db, and this will show us that waiting for connections on port, the default port. Perfect. So this is an indication that MongoDB is up and running. You can inspect this pod with this command called kubectl describe pod db. And this will give us additional insights into how the pod is scheduled. For example, this will tell us the internal IP address of the pod is this. This is currently in running mode. This is the container ID created by Docker. And this is ready. The state is running. And you'll also notice that this is scheduled on one of the nodes. So everything seems to be clean. So the DB pod has been successfully created. But for the DB pod to become available to our web pod, we need to expose it. So how do we expose it? We open up a service, we create a service, which is going to act as a channel between the web pod and the database pod. So this is where I define a service. And this service is having these selectors called name Mongo. And this is how we are binding this service with the pod. So the label that says selector, name is Mongo is used by the selector, name is Mongo. So this is the binding and association and the contract between the service and the backend pod. So when the application says Kubernetes, I need to talk to DB, Kubernetes will check what is DB and hands over an IP address and a port, which is nothing but a proxy to our pod. The advantage of creating this intermediary is the decoupling factor. And remember, microservices are all about decoupling. So later on, if you have upgraded your code from MongoDB to Cassandra, everything remains the same. You will simply replace MongoDB pod with a Cassandra pod, and you will replace the web pod with the Cassandra driver, and everything works exactly the same. That's because we have this intermediary that is loosely coupling the web pod from the database pod. The database pod can run anything as long as the web pod can understand. We are not talking about database portability or standardization here. It is essentially how you manage one pod. Basically each pod can be thought of as a service. The other example is, let's say MongoDB comes out with a newer version with additional features. So you can very quickly apply that without disrupting your application, all by adding, for example, MongoDB latest, right? So when you use this, you're basically pulling the latest image. So you can very quickly upgrade one of these pods without disrupting the rest of the application. That is the advantage of using a pod plus a service combination. So the service is the proxy that will abstract the underlying pod. So it's time for us to create our service. So kubectl create from file db service.yaml. And now we can check the service. So it is called cluster IP because we want this to be exposed only internally to the pods. Database should never be exposed to the outside world. No one should be able to talk to the database directly. So we expose this within the cluster, and that's why it gets a cluster IP. This is the cluster IP. And it is exposed on port 27017. Perfect. So now we have the database pod and the database service. So technically our backend is in place. Now it's time for us to create the web pod. So how does the web pod look like? Not very different. It is exactly how the database pod is designed or declared. The only difference is the image and the port. So I'm pulling the image that I push to Docker Hub, which is Janakiram m/todo. I gave the container name as my web, and by default Express framework listens on port 3000. I'm not going to change that, so I'll expose this pod at 3000, and I define the labels with the name web, app is to do app, consistent with my database pod. All right, so let's go ahead and create our web pod. Okay, now we'll end up having 2 pods. So let's wait for this to finish. Actually, it's not required, but I want to show you how the status changes in a few seconds. So currently what is happening is Kubernetes is pulling the to-do image. There we go. Now it is in running mode for last 18 seconds. Perfect. Once the web pod is in place, we need to make it available to the outside world. How do we do that? Well, again, we'll define a service. So this is the service, and how does this service know which pod to talk to? Again, we have the selector name is equal to web, and here we have name is equal to web. That's how this service knows how to talk to the backend pod. So we define that, and then the key thing here is we are mentioning type is node port, which is different from the database. Here we are defining the type as cluster IP. The fundamental difference between cluster IP and node port is node port is meant for outside world. This is going to be made available on every node of your cluster, whereas cluster IP is confined just to the cluster. So the pods that are running within the cluster in the same namespace would be able to access that. But a node port will be publicly accessible. In fact, after I deploy this service, all of you who are watching this live can actually hit the IP address :port, and you'll be able to see the container to-do application because I'm going to expose the web pod as a node port. So nothing like seeing it live. So let's go ahead and deploy this as a service. So create -f web service.yaml. Excellent. Now we have 2 pods, one database, one web, and 2 services. Forget about the Kubernetes one. That's an internal default one. Don't bother about it. But we have the database as a cluster IP, and we have web as node port. And this 3000 is exposed to the outside world using this port, which is 32398. So now I'm eager to see how the application looks like. So how do I basically grab this? Well, go to the DigitalOcean console, right? Grab the IP address of one of the nodes. Okay, paste this and get the node port that is shown in kubectl get service and paste it here. And there we go. This is the live containers to-do application, and it is currently available on the worker node IP address : the node port port number that is shown here. That's it. Okay, now, oh, looks like someone is already adding to-do list to my task application. Great. I appreciate the participation. Oh, wow. Okay. Nothing like seeing it live and the app is working. All right. So I'm going to add this to-do called finish the demo. Okay. So this is great. And now we have a live app deployed as a microservice running in Kubernetes. That's not all. You know, while this is perfect, we are still running one instance of database, right? Look at this. We are running just one instance of the database. And no application should ever run as single instance. That is a single point of failure. So it's time for us to scale this application. So how do we scale? Well, Kubernetes has a primitive called replica set. No, don't confuse that with MongoDB replica set. That's a different thing. This replica set is a Kubernetes primitive where you can define how many number of pods you want to run at any given time. And that would ensure that even if one of the pods get killed for some reason, Kubernetes will bring back another pod to maintain the desired configuration. So it's time for me to kill the web pod with the delete command. Okay, now web pod is gone. If I do a refresh, there is nothing listening in the backend, so the service fails. I'm not surprised. But the service is left as it is. We are not killing this service. Web is still listening on port 32,398. We're not going to touch that, but we'll bring up a replica set instead of a pod. So now what I'm going to do is to show you a replica set. So a replica set is exactly like a pod. The only difference is you'll define how many replicas you want to run at any given point of time. So for availability, high availability, I'm basically running a couple of pods. And the entire definition looks very similar to the pod. It has a spec with container name, image, port. It also has the metadata labels. It also has the selectors, not exactly selector, but this metadata will help the service to automatically talk to the backend pods. So here we are defining at least 2 pods at any point of time. So now what we'll do is launch the replica set. So create -f web, not the pod, but the replica set. And now when we do a get pods, we'll notice that Kubernetes has added a random arbitrary name to web. That is because every pod got to be unique. So now we have a slightly better architecture, right? 2 web pods and 1 database. So let's go back and do a refresh. Wow. Okay, now you'll get back everything. That's because the database was intact, the service was intact. We simply killed one of the pods and brought back a replica set. So now everything works like a charm, right? That's the beauty of microservices. That's not all. Now look at this magic. Okay, what I'm going to do is to run this in 2 windows. So I'll split my screen. Here I'm going to run kubectl get pods in watch mode. Okay, so this will show us how many pods. Okay, I need to do the kube config. Okay, so now we'll actually see the 3 pods running. Now how about this? I want to run 10 instances of the web pod. How quickly can I do that? With just 1 command, right? So keep an eye on the bottom window. So kubectl scale replica set called web. How many replicas do you want? 10. Okay, now it says replica set web scale, and here look at this. It very quickly started creating 10 pods for us, right? So in just a few seconds, everything will be in running mode, which means our web application is now scaled from 2 to 10 in no time. In just about 30 seconds, the average age, everything 26 seconds, perfect, right? So now we have 10 instances of the web app and 1 instance of the database. How are we doing? So let me do a refresh. Super. Okay, everything is perfect. So this is how you scale. I can actually go ahead and scale this to 20, but that would put some pressure on the cluster, and that might create some issues. I'm not doing it. But let's say, I'm one of the e-commerce portal, and I launched the latest mobile phone, Xiaomi, and it is exclusively available on my portal. There is a flash sale. So I have gone ahead and scaled my web pods. And now the flash sale is done. We sold like 20,000 new phones, and I don't want to keep the web pods running like 10 replicas. So I want to bring it back to my baseline, which is 2. So just go ahead and hit kubectl rs web replicas 2, and now you'll notice that everything is terminating. And in just 30 seconds, we'll be back to the baseline configuration of 2 pods. Because every pod consumes resources, we don't want to leave them running forever. So once the traffic subsides and once the load comes down, I want to go ahead and bring it back to our normal baseline configuration, desired configuration, which is just 2. So in a couple of minutes, everything will become normal, and you'll notice that we'll have just 3 pods, and there we go. 1 database pod and 2 web pods. And nothing changes here. The performance is exactly the same, right? So Oh, someone from Nigeria. Hello from Nigeria. Hi from India, right? Thanks for joining us. I really appreciate it. I really like seeing people from all over the world joining my sessions. Great. All right. So that's how quickly you scale your web pods. So that was the demo that I wanted to show you. But if you're wondering, is this production ready? Well, it's not really production ready. And there is one bottleneck. There is one major issue that we need to resolve before we go live. And that is the single point of failure with the database. While I've been conveniently playing around with the web pods by scaling them from 2 to 10 and bringing them back to 2, I'm not touching database. The reason is it is stateful, and you cannot tinker with databases like the way you tinker with web pods, because it is stateful, and every time I launch a new DB, it will create another database, and it is my job to keep them in sync. So it's going to be a pain. So we have to be very cautious when we are running stateful services. So how do we make this application production ready? How do we make this more robust and make sure that we have a full-fledged, full-blown, best practices driven application? Well, we need to turn the database into what is called as stateful set. And that is the theme for the last webinar, which is scheduled for April 2nd or 3rd. You will actually get a notification. So there I'm going to cover how we take this app and make the database layer more durable, more reliable, and more scalable. So we'll turn the database pod into a stateful set where we'll run 3 MongoDB replica sets. And in that case, even if you kill one of the database pods, because it's a part of what is called as a stateful set, everything will come back. So that is the beauty. By the way, I will show you one more interesting feature. So now that we are running 2, what happens if one of the pods get killed, right? So kubectl delete pod, and I'm going to go ahead and kill this, and this is terminating. As soon as this is terminating, you will see another pod coming up, and that becomes instantly that moves into running mode, right? So container creating, and very quickly you will see it's going to be in running mode, and this will be completely gone. So what I want to demonstrate here is with replica set, you always maintain the baseline configuration, the desired state, which is two pods. That is the replica set that we created. Now, unfortunately, you can't do the same thing with the database. If for some reason I go ahead and do a kubectl delete pod db, poof, everything is gone, and we cannot get it back so easily. And that too, we are not using a persistent backend. So this is a single point of failure and a very fragile architecture. So next webinar, don't miss, because it's going to be taking this application to production, to live, by using okay, before my cluster gives up, let me delete the resources. So we are now starting with the web RS, then the web service, followed by the DB pod, followed by the DB service. So this is basically how we do a cleanup. So now all the resources that we created during this, they get deleted. And sorry to disappoint you, but you can't access this anymore. It was just a demo. So let me take you back and do a quick summary, right? So this is a quick summary of what we have discussed so far. Cluster, pool of compute, storage, and network resources. Nodes are the host machines. Namespaces are logical partitions. This was extensively covered in the last webinar, but I want to do a quick recap because we touched some of these aspects in this webinar as well. Pods are the unit of deployment. We packaged our node.js app as a pod, MongoDB as a pod. Labels are the key value pairs, use it for service discovery. That's how the DB service and the web service discovered their respective pods. Replica set ensures availability and scalability. Even after I killed one of the pods deliberately, it brought it back. Deployment manages the app lifecycle better. This demo didn't cover deployment, but you can explore, you can convert the replica set into a deployment, and it comes with additional features. So some of the interesting commands that I touched upon, and you may want to learn more. kubectl create, this is the most important command. If you want to create any Kubernetes object, you start with create. Get is to access. Describe is to inspect any object that you created. Scale is applicable to a replica set or replication controller. kubectl delete is how you get rid of your artifacts and resources. I went through all of this. You can learn further from the Kubernetes official documentation. And this is just a subset of the commands that we'll use throughout this series, and also managing Kubernetes in real world. All right, so that brings us to the end of this session.